How's it going? I'm still working on this baseball game for my video game physics class. Right now we're at a fairly good point, if I can figure out where my mouse is, where we can just look at this and see that I have both players, both the pitcher who's going to pitch the ball randomly when I press start, and the batter who's going to respond to my key presses. And, you know, we have something like that. We've animated both of them. Now, what I'd like to do is I'd like to introduce forces. So far, the only real physicsy thing we have right now is a reflection, or of deflection, excuse me, which is just where we reverse the sign of the velocity when something hits something else. So just like that, when I hit the ball with the bat, its velocity reverses. That's not really the best model for a baseball bat hitting a baseball, but it is probably the simplest and good enough for now. When I introduce two-dimensional stuff, I'll introduce some more complicated stuff. First, I'll introduce the normal and tangential components and stuff like that. Then I'll introduce probably some more complicated stuff as far as the collisions are concerned. But right now, this is all we're really doing. We're modeling the collision at the bat, and we're modeling forces for the ball in between the pitcher and the batter. Right now, we don't have any forces in stock, so let's start adding some. Now, gravity, which is the sort of normal the thing you usually think about as far as all of the forces are concerned, that's the first one you're introduced to in Physics 1. I've got some issues with that, but you know, I'd have issues with what I'm going to do, which is air resistance as well. But air resistance is going to keep our problem linear. It's all going to be in the x direction until a little bit later on when we go to 2 dimensions. So we're going to keep everything linear with the air resistance right now. And that should be something that makes things easier for us. So one thing I'd like to do before I introduce the air resistance is just go ahead and put this print statement in. The print statement is going to let me just show you that when I throw the ball, right, the speed of the ball doesn't change. It's at minus 132 feet per second. Minus means it's going left, and 132 just means feet per second. That's its rate. The problem is that unless I play with numbers, and I probably will play with the numbers, there will not be a visible effect. So it's still going to go really, really fast. So yeah, it's starting out at 90 degrees or 90 miles per hour. It's probably going to be at about 81, 80 miles per hour when it hits here. That's still really fast, right? And you know, you've got this small screen to look at it on. So it's probably not going to be visible until I play with the numbers. But when it is going to affect things, and it's going to affect things at approximately the same level as gravity. That's more or less what I found out. So I'm going to keep that print statement in there so that you can see what the changes are later on while I do these changes. I think I'm going to have to break this up into 2 different videos. I already tried one video and it got halfway through, and I got all the way through the 15 minutes allocated, and I really wasn't there. I was just getting ready to add in the air resistance. So what I think we'll do first is just try to modify the baseball, figure out what sort of things we have to do to the baseball to let it have forces act on it. All right. And then what we'll do is we'll go and move into the pitcher and the air resistance function. We'll write an air resistance function here. Probably better to use a class, but we're going to keep objects in this game, or in this class. We're using objects only for physical objects. Later on, we'll move that out when we get to the mythical unit 5. But first, we'll go ahead and just keep with our idea that objects are things and things only, just for a pedagogical device. Let's see, what do I want to do? Okay, so I want to add forces. So what does a force do? Force creates an acceleration, which means it modifies the velocity. So we're just going to modify the x velocity right now, and that's going to have to be dependent on an acceleration, or more precisely the force, right? and the force is going to be the mass times the acceleration. So to get the acceleration, we'll have to divide by a mass there, and then we'll multiply that by the interval. Multiplying the force by the interval is the impulse, is what we call it in Physics 1, and that's what we add in technically each time we do this step, is an impulse, a change in the momentum. And we change the momentum, and then we change the velocity to match that. So that's what we're going to have to do, and we're going to keep track of forces every step. So we're going to add in all the forces every step, assuming that the forces can change. In fact, this particular force does change because it's going to be dependent on the velocity, and it's going to slow the velocity down. So just by acting, it's going to change its magnitude as we go along. So we're going to want to do something like clear out the force at the end of each update. Okay, so now you see we've got two new things that the ball has to keep track of. So it has two more properties that have to keep changing. One is going to be the mass, which is something that's not, well, it's not going to change, but it's something that has to be kept track of in here. And the other is the force, right? And we're going to start off by initializing those two, both the x and the y, just like v and the position and the velocity of x and y components. We're going to keep all of those at 0, both of those components at 0, and we'll modify them as we need them. But now we have a mass that we're sending in here. We're going to have to send a mass in as well when we initialize this ball. So that is going to require a small change elsewhere. So actually, I guess I'll go ahead and make sure that when the pitcher pitches the ball, is this the pitcher or is this the batter? That is the pitcher. He throws the ball. So he's going to have a mass in here. That's the mass of the ball. Or I could just put it in the ball class. It's always 0.32 pounds. And then we put the mass in here. And hopefully, if that's fine, so far there should be no problem. So I'm just going to run it and make sure that I haven't broken anything. And it looks like it doesn't break anything. I'd know it broke something if when he's at the middle of his pitch, right after he throws the ball, the program crashes. So that's the most likely place for that to for something bad to happen. So what's next? Well, we need to do something with these forces. We need to get the forces into the ball, right? Right now, there's nothing going on here as far as the ball is concerned. What we'll want to do is add in forces, right? So let's see, how would I do that? I'm going to do this by adding the force individually each turn from the engine. Probably a good idea would be to just pass in these forces and save them, right? So we could save the force that's operating on this particular thing. But then I'd need to make a list of forces, and we'd have to do all sorts of fun things. And it would work. It would just take a little longer. It would be better, but it would take longer. So we need to get a force. And our force, so we're going to want to get the result of this force, which is going to be a function. It's going to just look at the ball, but we've got a force on ourself. Yeah, let's do that, force on. So the force is the force on ourself. And so this whole ball is going to get sent to the physics engine. All right. And once in the physics engine will calculate things basically in this air resistance or later on in the gravity fields or functions, and those will come back here, and then we'll update these. We'll update the force, the total force in this particular in this particular ball each time that happens. So the x component is the 0 component of f, and the y component is the 1 component. Okay, so that should do it. I'll just call this add force each time, and that will call whatever function I tell it to call, and that needs to know stuff about this particular object. And that means I'm going to have to add more get methods, right? So what sort of things could my force want to know about? Well, it might want to know about mass. My gravitational force is going to want to know about mass. Could want to know about velocity. This guy's going to want to know about velocity. Could want to know about the radius. Again, that guy, our air resistance function will want to know about the radius. So we need to make get functions for all of these, right? Probably, usually, what you really want to have these available earlier on, but of course I'm trying to hack together 15 minutes worth of stuff at a time, so I usually don't have any extra time at the end of these things. So I could do def get radius, right? That's something I could do. It's probably useful for certain things. I think the collision algorithm might use it, but I think the collision algorithm's in here, or the collision detection. Then another thing we could add in here would be get the cross-sectional area, right? And the cross-sectional area is going to be equal to pi times the square of the radius. So it's possible that we'd want to use that, and it's also possible that we might want a volume, right? And the volume is going to be 4/3 times pi times r cubed. Now, the issue here now is that I'm using this constant math.pi, which comes from the math package. I could either just import math, or I could type 3.14159. That's probably going to be sufficient for whatever we do in this class, but the math package has a much better value for pi. So I think that doesn't break anything yet. And no breakage, and so far no changes in the velocity. The velocity stays the same no matter how many times I run it, and that's going to change in the next video when I add in the force. Now, I think I have about a minute, so I'll just talk a little bit about why did I add in the area and the volume. Well, a force, depending on the force, it could use different, variables. If we had to worry about the buoyancy, I don't think we want to or have to worry about the buoyancy of the baseball in the air, but we could worry about that. If we wanted to worry about that, then we'd need to use the volume, right? We've got an area function here. That's going to be important because we do need the cross-sectional area. This is the cross-sectional area, not the surface area. Possibly we could use the surface area as well. Then I'd have to remember what that is. I think it's 4 pi r squared, but I'm not sure, so I'm going to just lay off of that. So any of these could be used. In fact, the volume I just threw in for fun. And I think as far as the, I think that will be sufficient. Now, I may fail in the next one. I think we've got everything we actually need to do in the picture. So I'll come back and I'll try to do the air resistance and see if that actually works out. All right, thanks.